Okay. What we're going to do today is continue introducing material in chapter 15, which will be part of the exam number 6. And this is part 2. Last Tuesday, we finished up part 1 at dilution. How do you do a dilution from a concentrated stock to a more diluted working solution? And that's where this slide is. So next, we're going to talk about stoichiometry using solutions. The last time we talked about stoichiometry, we were focused primarily on masses. We would have a balanced equation and let's see. Well, let's just use a generic equation. So you got reactants and products, and we were given the masses, right? So many grams of this, so many grams of that. And we had to determine which one was limiting. And then before we could move to answer a question about the products, we had to convert. In fact, in the process of determining the limiting reactant, we had to convert to moles, right? And the conversion factor for each one of those would be their respective molar masses. All right, so once the equation is balanced and you've made these conversions, then you can move from here over to products and determine the outcome. But all reactants aren't necessarily given to you in units of mass. Sometimes you are mixing solutions, and the solutions are of a known concentration, usually molarity, and a given volume. And we know from our equation, molarity equals moles per unit volume. We can solve for moles. So if you know the molarity of the solution and its volume, you can calculate the number of moles of reactant. So you can get to here, not by using mass and not by using molar masses, but by using concentration and the volume that is being combined in the reaction mixture. So this is a list of steps that you would follow to solve a stoichiometry problem where solutions are involved. But I put these in here just for posterity. What we're going to do is work problems, and then these steps will become obvious. We basically do the same thing that we did with mass stoichiometry, except the moles are determined by molarity and volume rather than mass and conversion using molar masses. So there's just a slight difference between the two. Now, if you need to convert, once you find out how much product is produced, if the question is, what's the mass of the product, then you would take the moles of your product and use molar mass to convert it back to mass. That would also answer the question. But the question may very well be, what's the concentration of this product in the resulting solution? Right? That's two possibilities. All right. So let's take this problem. 10 milliliters of 0.3 molar sodium phosphate solution is reacted with 20 milliliters of 0.2 molar lead 2 nitrate solution. Okay. And what that last statement means, assume no volume change. When you add two solutions together, there's no guarantee that the total volume will be the sum of the two individual volumes that you add together. Sometimes the volume increases, sometimes the volume decreases. But for the purposes here of simplicity, we're going to stipulate that the volume does not change when we add them together. Okay, the reaction then. First thing you need to do is write the compounds correctly from their names. Sodium phosphate. Right? There's sodium. There's phosphate. And we know that phosphate is a polyatomic ion with a 3- charge. Sodium is an alkali metal with a +1 charge. So we need 3 of them to correctly write the formula. And this is in aqueous solution. Then we're going to add to that a solution of lead-2 nitrate. Right? That tells us that the charge on lead is 2+, and nitrate is a polyatomic ion with a -1 charge. So in order to balance this one, we need 2 negatives to balance that 2 positive. Right? So now we've got these written correctly. And let's see. 10 milliliters of 0.3 molar sodium phosphate. So 0.3 molar sodium phosphate, and we have 10 milliliters of this solution. And then we're going to add to that 20 milliliters of 0.2 molar. Okay, that's everything that's given so far. The question is, what precipitate will form? What we need is to reference the solubility chart that was given to you in a previous chapter. And let's see, I think I have a copy of it here. Yes. In your review document for this chapter, in useful information, there's a copy of the solubility chart. That means it will also be available on exams. But if you're taking your exam in Brightspace, there'll be a separate document in the exam folder with this information in it. And just as a reminder, you need to make a copy of that if you don't already have a copy of that document with this information in it before you start the exam. Because once Lockdown Browser gets hold of your exam, it won't let you access any of that other information. Okay, so remember this is our solubility chart, right? Cations across the top, anions down the left-hand side, and we find the intersection of the two to determine if a combination of a positive and a negative ion will produce a soluble compound or a precipitate. So how do we determine the precipitate here? Well, we treat it as a double replacement reaction. In other words, this cation, once they're in solution together, this cation has access to that anion. So we write those as a possible product. Sodium nitrate. All right. Sodium's a +1 charge, nitrate is a -1 charge, so we only need 1 of each. And then we look it up here, sodium and nitrate, and find that this is a soluble compound. The other possibility is lead 2+ and phosphate 3-. So I'm going to have to write it down here. Right, lead 2+ and phosphate 3-. So remember how we balance those equations, those formula. When you have an even numbered positive ion in this case, and a odd numbered negative ion, cross multiply. In other words, this 3 comes over here, this 2 goes over there. And that balances the formula. Then we look it up in our chart. We look up lead 2 plus, which is over here on the far right-hand side. And then we follow it down till we find the phosphate. And we find that that block is grayed out. That means this is insoluble. This compound forms a precipitate. All right. So that answers this question. Well, the second question is, how much of that precipitate is formed? What mass? Since it forms a solid, then our natural choice is mass. All right, so we need to determine the mass of that solid. All right, so next step is to determine where you're going, find out what the precipitate is. Then you combine the ions to determine, we've already done that step. And then we balance the equation in molecular form, just like this. All right. Remember, if we set up a budget, since we have polyatomic here unchanged, we can use that as a balancing unit. Same for nitrate. The nice thing about these double replacement precipitation reactions is they're very easy to balance. And in most cases, we don't even need to set up a budget. So I would look at 3 sodiums. We need 3 sodiums. So we put a 3 right there, 3 sodiums. That means we have 3 nitrates. All right, let's wait just a second and go for lead. We need 3 leads. 3 leads, okay? So that gives us 3 leads, and we need 2 phosphates, right? So now we have 2 phosphates, and we have 6 sodiums. So now we have to change this to 6. Okay? So 6 sodiums, 2 phosphates, 3 leads, and 6 nitrates. 6 nitrates. That is balanced. Coefficients of 2, 3, 6, and 1. Now that we have a balanced equation, we can determine the moles of the reactants present in solution, plus we need to determine which one is limiting. All right. So the moles here would be volume times molarity. All right. Now, here's a little trick I'm going to show you. We can either convert this to liters to determine moles, which is probably what we should do. But we can also multiply these two together, and instead of getting moles, we get millimoles. So if we convert this to liters, right, 3 places, 0.0100 liters. If we calculate millimoles, it'd be 10 times that would be 3.00 millimoles. Or if we multiply this one times 0.3, we would get 0.0300 moles. Notice that millimoles, this milli is 10 to the minus 3. So 10 to the minus 3 would be 3 places to the left. 1, 2, 3. And that's not right. This should be there. All right. 1, 2, 3. Yes. Okay. So we are going to need moles. And the reason we're going to need moles is because we have to know the number of moles of the product in order to convert it to mass. Now, millimoles will be more convenient for calculations and finding out which one is limiting, but eventually we're going to need to know moles. Well, if we do the same thing here, we get 20 times 0.4 is 4 millimoles. And then if we convert that, 0.00400 moles. Okay. So now that we have the moles of sodium phosphate and moles of lead-2 nitrate, we can find out how many moles would each one produce if all of it were consumed. And then the one that produces the least amount of product is the limiting. So if we convert this one, 0.00300 moles, and this is sodium phosphate, then we need a conversion factor to convert sodium phosphate to lead-2 phosphate. Okay, and the coefficient is 1 and 2. So that means we would get 1/2 of this value, 0.00150 moles of lead-2 phosphate. Okay. That's if all of this were used up. That's what we would get. Then we want to convert this one, which is lead-2 nitrate. We want to convert it to lead-2 phosphate. And the coefficient is 1 to 3. So 1/3 of 0.004.
Let me get my calculator.
Let's see, 0.004, enter, and 3 divide is 0.00133. And this would be moles of lead-2 phosphate. Okay, now we compare the outcome. Which one is limiting? This one produces 0.0015. This is 0.0013. This reactant produces a smaller amount of product. That means this one is limiting. And this one is excess. Right, so which reactant is limiting? We determined that. And then we're going to calculate how many moles of, well, we already did. To determine a limiting one, we did calculate the number of moles that would form. So now we have the number of moles of this form. All we have to do now is convert it back to mass. Okay? So if we take that value, let's see, let's put it down here. 0.00133 moles of lead-2 phosphate. Then we need to cancel the moles and leave us with grams. So we need to know the molar mass of lead-2 phosphate. That's where you go to the periodic table and you look up lead. Lead is 207.21, 207.21 grams per mole. Right, this is lead. But you have 3 of them. Okay. Then you have 2 phosphorus. 30.97 grams per mole. And then we have how many oxygen? 2 times 4 is 8. We have 8 oxygen, which is 16 each. And we add those together. And I get 811.57 grams per mole. That's the molar mass of lead 2 phosphate. Times 0.001333, which is 1.08. See, 3 significant figures. Let's see. Let's go back. No, 2 significant figures. Okay. So there we have our equation balanced, and we're determining the precipitate, which is lead 2 phosphate, and the mass of the precipitate, which will form after we balance the equation. We find the limiting reactant. All right. Then we take the limiting reactant and convert it to next step, convert it to mass, grams of lead 2 phosphate. Solid. Okay. That seems like an awful lot of trouble, but those are the steps that you must learn and master to solve this type of problem. And this is stoichiometry in solutions. All right. Same reaction, different question. What is the concentration of nitrate ions that are in solution when the reaction is complete? All right. You start off with this much nitrate. We can calculate the amount of nitrate in solution. Is there any left in solution when we get finished with the reaction? Yes. All of it is there because nitrate is not precipitated. It's in solution before, it's in solution after. The only thing that changed, the number of moles of nitrate did not change. We added a certain amount of nitrate, it's still there. The thing that changed is the volume. All right. So let's make a little room over here on this side. And we can calculate the number of millimoles of this compound is 4 millimoles. Right? I'm going to work with millimoles now, and I'll explain it to you as I go. Millimoles of that compound. How many millimoles of nitrate do we have? Well, for every 1 millimole of that compound, we have 2 nitrates. That means we have 8 millimoles of nitrate. Of nitrate ions. Now, what's the volume? The volume is 20 plus 10, or 30 milliliters. All right. Notice that if we factor out the milli, right, the millis cancel, and we have moles per liter. So what I'm saying is if you divide millimoles by milliliters, you will get molarity. So let's finish dividing that out. 8 divided by 30 is 0.27, 0.27. I see 3 significant figures. 267. 0.267 molar nitrate. All right. That's the concentration of nitrate ions in the final solution. Nitrate is what we refer to as a spectator ion. In other words, it does not participate in the reaction. The reaction is between phosphate and lead. Nitrate and sodium are both spectators. Right? 0.27. Actually, we have 3 significant figures. So this is, let's see. 1, 2. No, we have 2 significant figures. They are right. It should be 2. This is 8. No, I'm right. 6, 7. No, that's correct. That's correct. 0.267 molar in nitrate. All right. Now, here's a little more difficult question. What's the concentration of phosphate ions that remain in solution? Notice, this is the limiting reactant, lead 2 nitrate. All of that lead is going to be consumed in the reaction. But this one is excess. That means only part of the phosphate will be used, and we will have some phosphate left over. All right. Well, the way to solve this question, what's the concentration of phosphate ions, is to find out how many we started with, how much we used, subtract it, and that's what we're left over. That's what's remaining divided by the total volume will give us the concentration of phosphate. Okay? So, how much phosphate do we begin with? We have, for every 1 unit here, we have 1 phosphate. So we start off with 3 millimolar phosphate. This is initial. Okay? How much is used? How much is used is what we have over here. Right here. Let's see. This is the moles of lead 2 phosphate. This is how much is used. Let's convert this to millimole. 1, 2, 3. 1.333 millimoles of that compound. So if we have 1 1/3 millimoles, of the compound, how many millimoles of phosphate do you have? For every 1 of these, you have 2 phosphates. So times 2 equals 2.666 millimoles of phosphate. Okay, so that's how much was used. 2.666 millimoles of phosphate were used. That means we're left with, let's see, 1.333 millimoles remain. Now that we know how much is left in solution, we just divide it by the total volume. Remember, millimoles divided by milliliters, which is what? 10 plus 20 is 30. And that will give us the concentration of phosphate that remains in solution. And let's see. Well, in scientific notation, it's 4.44 times 10 to the minus 2 molar. I'm not sure how the expression goes in the answer here. Okay. Oh, my mistake. That was a serious error. I can't even subtract. Right? 6. I borrowed from this one, so that's a 0. Let's try that calculation again. There we go. 1.11 times 10 to the minus 2 molar. There, that's more believable. 0.01. Yeah. Or in standard notation, move the decimal place. In phosphate. Left in solution. All right. So that's solution stoichiometry. Now let's talk about acid-base reactions, neutralization reactions. We can still view the neutralization reaction as a stoichiometry problem. And I'll explain in just a second what I mean by that. We need a driving force, something that drives the reaction to the right. In our previous example, we had a precipitation reaction that was driving the reaction toward the manufacture of a solid. In an acid-base reaction or a neutralization reaction, the net ionic equation, let's start with an example. All right, let's say we have sodium hydroxide. And we're going to neutralize acetic acid, vinegar, acetic acid. Okay. So what are the products here? Well, double replacement says that sodium, the cation goes with the anion. And we look that up in our solubility chart and find that that is soluble. All sodium salts are soluble. What's left over? Well, we have a hydrogen and a hydroxyl, which means we have water. Remember, acid-base reactions always. A base, an acid and a base produce a salt and water. Now, in this case, the salt is soluble. Some acid-base reactions produce insoluble products, but they always produce, they always react to produce water. Okay? If this is soluble, then the hydroxyls are in solution. And the acetates, the hydrogens are in solution, reacting with this. These are spectators. That's a spectator, that's a spectator. They're spectators. Okay, so the net ionic equation for an acid-base reaction is always hydrogen ions plus hydroxyl ions yields water. The formation of water is the driving force for an acid-base reaction because hydrogen and hydroxyl really, really want to get together. So the reaction is essentially all the way to the right. Okay. Let's say we're going to titrate sulfuric acid and sodium hydroxide. Right? So we need a different equation. Here, we need that. And we need this. Well, sulfate is a 2- charge and sodium's only a 1+. So we need 2 of these. Okay. That means we need 2 of those. 2 sodiums, 1 sulfate, 2 hydroxyls, and 2 hydrogens. Yield 2 water. So we need a 2 here. That balances the equation. All right. What are we given? How many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar sulfuric acid? 0.5 molar and 1 liter. So if we multiply, and the question is, how many moles of sodium hydroxide are required? Okay. If we multiply molarity times volume, we get moles. So this would be 0.5 moles of sulfuric acid. Okay. So how many moles of sodium hydroxide are required? All we need is a conversion factor. Right? H2SO4. So what's the ratio? Well, we have 1 of these and 2 of those. So that equals 1.00 moles of sodium hydroxide. That's how many moles of sodium hydroxide are required to react stoichiometrically, exactly the right amount in that solution. And there you go. All right, now this discussion centers on a new unit of measure called normality. So when we say normality, we're usually talking about acids and bases, but not always. What we're talking about is units of ions. When we say normality, we're saying normality rather than moles per liter, we're saying equivalents per liter. So what's an equivalent? Well, in terms of acid-base reactions, if we say 1 equivalent of acid, we want to know the amount of acid that produces 1 mole of hydrogen ions. Okay. So example? Well, for the base, it's the same concept, only with hydroxyls. All right, we'll get to equivalent weight in just a second. So, how many equivalents, if we have 1 mole, actually, if we have 1 mole of sodium hydroxide, how many equivalents is that? Well, 1 mole of sodium hydroxide produces 1 mole of hydroxyls. So 1 mole of sodium hydroxide is 1 equivalent of sodium hydroxide. 0.5 moles of sulfuric acid produces how many moles of hydrogen ions? It produces twice that many, right? So we could view it as a dimensional analysis problem and say, how many equivalents of hydrogen ions are produced? Well, for every 1 mole of acid, you get 2 equivalents. So 0.5 molar, 1 liter of 0.5 molar H2SO4 actually produces 1 equivalent of hydrogen ions. So, what is the normality of this solution? If we have 1 equivalent per liter, that is 1 normal. And for the acid, we have 1 equivalent of hydrogen, which would be the same thing. Okay. So we've determined that this solution in combination with that of sodium hydroxide in combination with that solution of acid are the same normality. Now, sometimes we're given the mass of some compound, and we want to know what its equivalent weight is. And that depends on how many moles of ions that it produces per mole of molecule. So the mass in grams of 1 equivalent of acid or base would tell us that. All right. So what is the molar mass of sodium hydroxide? Well, let's see. Sodium is 23 and 16 for oxygen and 1.01 for hydrogen. So that's let's see, 10, that's 4.01 grams per mole. Sulfuric acid would be 2.02 for the hydrogens. Sulfur is 3207. And 4 oxygens is 64. Right, so we have 9, 0, 6, 7, 8, and 9. 98 grams per mole of sulfuric acid. All right. What's the equivalent weight? Well, the mass of sodium hydroxide that produces 1 equivalent is 40.01 grams. Right? Because if you have that many grams of this compound, you're only producing 1 equivalent of hydroxyls. So in this case, the equivalent weight is the same as the molar mass. However, for the acid, 98.08 grams of this acid will produce 1 mole of the compound, but 2 equivalents of hydrogen. So we only need half the weight of sulfuric acid to produce 1 equivalent of hydrogen. That means we divide by 2 and we get 49.45. Yeah, 0.45 grams per equivalent. So the equivalent weight of sulfuric acid is half the molar mass, because for each mole, it produces 2 hydrogens. And that's the rule of thumb. If you determine the molar mass of a compound, acid or base, and you find out it produces 2, 3, or 4, however many hydrogens, or 2, 3, or 4 hydroxyls, you just take that number and divide it into the molar mass, and that gives you the equivalent mass, or the equivalent weight. All right. So this is an explanation in picture form that I just gave you in verbal form. 1 mole of sulfuric acid produces 2 moles of hydrogen. So 1/2 of the sulfuric acid will produce 1 mole of hydrogen. Okay. So here's an illustration that comes out of your textbook in chapter 15. The molar mass of hydrogen chloride is 36.5. Its equivalent weight is 36.5 because it produces 1 hydrogen per molecule. Nitric acid would be the same way. Sulfuric is the one we illustrated here. Bases, similarly, sodium hydroxide, potassium hydroxide, their equivalent weights are going to be exactly the same as their molar masses because they only produce 1 hydroxyl per molecule. Okay. Then when you calculate normality, you need the number of equivalents in the solution divided by the volume. Now, why are we going to all this trouble? Well, if you know the equivalence of an acid and a base, you don't need to know the stoichiometry, you don't need to know the balanced equation. All you need to know is the normality of each one and the volume of each one. Okay. So if barium hydroxide is the base, how many equivalents of barium hydroxide are there in 4 moles of barium hydroxide? Well, if you have 4 moles of the compound, for each mole of the compound, you have 2 moles of hydroxyl. So 2 times 4 is 8. You have 8 equivalents of hydroxyls. All right? Okay. Now, if you work day in and day out with acid-base reactions, right? If that's your job description, once you got your degree and you got a job with some company or some government lab, and you work with acids and bases day in and day out, then this way of expressing concentration is extremely useful. If you only use acid-base reactions periodically, right, then we can go back to the balanced equation and work everything from there. And there's no problem. So it depends on your job description and how many of these analyses you have to do in one day. You have to do a lot of them. You have to do 100 of them. Then normality would become extremely useful. And if you have mixtures of acid-base reactions in the day, normality would take this part of the calculation out of the picture. If you know the normality of your acid and your base, you don't need to know what they are, unless they produce a precipitate, and then that's another question. So we're done with chapter 15. And what we'll do, we're done early with chapter 15. What we'll do is next Tuesday, we'll take that review document and look at some representative problems to get you ready for the next exam.